If you like to roll the dice and move your marker, then you should like learning about finite state machines. We're first going to learn about state diagrams, and the concept is no different from that of a board game with a marker where the input will determine where you move next, and the current square you're on determines what the output is going to be. There are two types of finite state machines. A Moore Finite State Machine has the property that the output only depends on the current state, and that will be explained presently. The more general finite state machine is the Mealy Finite State Machine, which does not have that limitation. In both cases, a state diagram involves nodes, which are denoted by circles, and transitions between different nodes, denoted by arcs, like this. For a Moore finite state machine, we label the node by giving it a name, so it could be a letter, a name, a number, whatever. So this is state A, and we draw a line, and underneath state A we represent the output. It depends how many bits of output we have. If we have a 3-bit output, then I need to put a 3-bit number for this state. The number of bits on the output is always going to be the same. Down here gives this state a name, state B, indicate the output if I'm in this state here. And then this transition here tells me if I am currently in state A and I get a certain input, then I'm going to follow this transition. So I need to know how many different inputs we can have. If we have a 2-bit input, then that means that I can label this transition 1, 0, meaning if my 2 bits of input are a 1 and a 0, I move along this transition here. I need to explain what to do for all the other possible inputs. So I'll have another transition here if the inputs are 0, 0, another one here if the input is 0, 1, and another one here if the input is a 1, 1. And this is true for all my states. Clearly, this is not a complete diagram. For a Mealy finite state machine, it's very similar. The nodes are labelled and they tell us the current state that we are in. Because the output of a Moore finite state machine only depends on the current state, then the output is written inside the node, inside the current state. However, for a Mealy finite state machine, the output can depend not only on the current state, but also on the input. Now, what comes next can be somewhat confusing if not explained to you. Assume this transition is labelled 10/110. Now, what does that actually mean? Two separate things are going on, and only one is related to actually taking this transition. So normally we are going to take this transition at a rising edge of the clock, which means that there might have been a rising edge of the clock. We've just arrived in state A, and we have to wait until the next rising edge of the clock before transitioning to B. Now, in this period before we transition, we need to know what the output is. And that's what this label is telling us. This label is telling us that if I'm in state A and the input is a 1, 0, then the output is going to be 1, 1, 0. Now I'll have other arcs coming out of here with different labels on them, and they will cover the 4 possible inputs. So when I'm in state A, I need to look at my 4 arcs coming out of state A. One will be labelled 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, or the 4 possible inputs. And based on the input when I'm in state A, I can read off what the corresponding output is going to be. That does not mean a transition has occurred. At the next rising edge of the clock, then you need to look at the current input, and if the current input is 1, 0, then you make this transition. So it's telling us 2 separate things. I can be in state A and the input can be changing, and that means that the output will change. Then at the next rising edge of the clock, when I make the transition, then my state is going to change. We're going to look at Mealy finite state machines in the next lecture. We're going to focus mainly in this course on Moore finite state machines. It is possible to convert between the two. There is perhaps a slight delay. You might lose a clock cycle. So a Mealy finite state machine is very general. A Moore is a restricted finite state machine. But usually the benefits outweigh the restrictions. So we normally use a Moore finite state machine. Let's look at this example. If we can understand a given state diagram, then basically we understand state diagrams. First, let's check that it is a valid state diagram. So what do we need? We need to have one node clearly labelled as the start node. Now how you do this is up to you. I've just written the word start here to indicate that we start at this node. Because it's a Moore finite state machine, then each node has to have the current state and the output when in that state. And the number of bits in the output needs to be the same throughout. You can't have a variable number of outputs in a digital circuit. Moreover, at each node, we have to have an outgoing transition for every possible input. In this case, the input is just a single bit, which means every node must have 2 outgoing transitions. The number of incoming ones doesn't matter, like this node has got about 4 incoming things to it, but that doesn't matter. The number of outgoing transitions has to equal the number of possible inputs, and there has to be a transition for each possible input. Now you can have a transition that goes to yourself, that's okay, but every single node has to have a transition for what happens when the input is a 0 and a transition for what happens if the input is a 1. Normally we don't use colours, but I've used colours here to make things very clear for you. And we see hopefully that every node has got 2 outgoing transitions, one in blue and one in red. Blue's for if 0's at the input, red is if 1's at the input. So it seems to be a valid finite state machine, or the states have got different names. It seems fine. So we've got our starting state here, and I've got my input here. And now it really is just like a board game. I start at the start, so I put my token here. Somehow I'm playing with a red shoe. Anyway, we start here. The output is going to be a 0 because we're in state A, and when we're in state A, the output's a 0. Now we see that our next input is a 0. So if we're currently in this state, if we get a 0, we follow the blue line. If we get a 1, we follow the red line. Well, we got a 0 for the input, so we follow the blue line. That means I move my marker down to this state here, B. And so I don't forget, I tick off this entry here, or cross it off. In my new state, where my red shoe is, I see that the output is a 0. So I update my output to be a 0 here. And then I wait for the next rising edge of the clock. My next input is a 0. So at the next rising edge of the clock, my marker, it does not take the red path. That's if the input's a 1. It takes the blue path. So at the next rising edge of the clock, I can cross this off and I move my marker to this state here. And I observe that my new output is going to be a 0. So I simply mark down 0 here. And repeat again. In this state, the next input is a 1, so I cross it off, and I need to remember to move my marker. I follow the 1 path. So I go over here, and my output is 0. Then for my next input, that's a 1 here, so I move my marker along the 1 path, and I get a 0 coming out, and I look at my next input, it's a 1, cross it out, move along the red path. Oh, something interesting. I get a 1 coming out here. Same thing, I have a 1 here, so cross it off. I move my marker, zoom, but I'm back to where I started from. That's fine, nothing wrong with that. And my output is still a 1. Next input's a 0, so guess what? Follow the blue one, and I get an output of 0. Next input's a 0, move this along here. Next output is a 0. Next input's a 0, move this along here, and my output is a 1 again. And we can go on forever if we so desire. And indeed, when you implement this in Verilog, that's all your FPGA, or that part of the FPGA, is going to be doing. It's just going to be following this diagram for the rest of its life. Hopefully I have convinced you that the concept of a finite state machine is very straightforward. It's just playing this board game with a marker, and it really is that simple in terms of the concept. What's a bit harder is trying to figure out what this finite state machine is actually doing. Is there a human explanation for what's going on, or did I just make this up randomly? Of course, the FPGA doesn't need to know why or how or where did it come from. The FPGA just plays this game and it's happy. But as engineers, we want to be able to understand someone else's finite state machine because we might have to extend on it or debug it or do something. And the other harder aspect is, given a real-world problem, to design a state machine for solving it. But in terms of the basic concept of a finite state machine, it's simply this, quite straightforward. All that remains is to connect it up with the keywords that we used in previous lectures. Remember, we spoke about the state, the next state logic, the output logic, and so forth. Well, the inputs are what we've been discussing. These are what cause what guide the transitions. The outputs depend on just the current state, and so the output logic is this mapping. The output logic is simply a truth table where on the left-hand side of the truth table is the current state, and on the right-hand side of the truth table is the output. So it's combinational logic, and the output logic simply tells us for the current state what's the output. The next state logic is given graphically by all these transitions. Again, it's a truth table. On the left-hand side of the truth table, we have our current state and the current input. So if I'm in state A and the inputs are 0, that's on the left-hand side of my truth table. And then the right-hand side of my truth table is where I go if I'm in A and the inputs are 0. And so the first row of my truth table will have a B at the output. If I'm in A and it's a 0, I go to B. If I'm in A and it's a 1, I go to E. That's the next state logic. In the Verilog code, we need some way of storing the current state, and we use flip-flops for that. And that means we have to associate some sort of a binary number with each state. But that's in principle easy to do. We can just make up a simple ordering. We have got 1, 2, 3, 4, 5, 6, 7 states here. So 3 bits is enough. I can say that this is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, and 1, 1, 0. That's pretty much it. A finite state machine is as simple as moving a red shoe around the state diagram.